A few meters below your feet, the ground can feel pleasantly cool even in summer. Go a few kilometers deeper, though, and the same planet becomes hot enough to boil water. Far below that, rock softens, metal flows, and the center of Earth reaches roughly 5,000 to 6,000 degrees Celsius. So why does going down eventually mean getting hotter? The first surprise is that underground is not one temperature zone. The soil just beneath a garden, the rock at the bottom of a mine, the mantle beneath a continent, and the iron core are heated in different ways and behave very differently. A cellar is not warm like a volcano. A cave often stays cool all year. Depth matters, but so does the kind of depth we are talking about. At the surface, the sun dominates. It heats the ground during the day and through summer, then the ground loses heat at night and in winter. Those swings fade as you go down. After several meters, daily weather barely matters, and deeper still, seasonal changes become weak. The temperature settles near the local yearly average. That is why basements and caves can feel cool in July and mild in January. Then the trend reverses. Below the zone controlled mainly by weather, temperature usually rises with depth. Geologists call this the geothermal gradient. In ordinary continental crust, a rough average is around 25 to 30 degrees Celsius per kilometer, although the number varies a lot. At 1 kilometer, rock might be a few tens of degrees warmer than the surface. At 3 kilometers, the extra heat can turn a poorly ventilated mine into a serious engineering problem. A worker does not need to touch glowing rock to notice it. Deep mines require powerful ventilation and cooling systems. Drilling equipment, electronics, lubricants, and even the cement around a well must tolerate temperatures that keep climbing. The cable, the pump, the rubber seal, boring parts fail first. That sounds minor, but it matters when the repair is several kilometers below ground. The geothermal gradient is not a universal ruler that can be extended all the way to Earth's center. If you multiplied 30 degrees by thousands of kilometers, you would get absurd temperatures. Different layers move heat differently. The crust transfers much of it by conduction, atom to atom. The mantle also moves heat through extremely slow convection. The outer core is a churning liquid metal. Each layer has its own pressure, composition, and physical behavior. Earth is also not a hollow shell around a global ocean of magma. Most of the mantle is solid rock. It can still flow, just very slowly, because it is hot and under enormous pressure. Over millions of years, solid mantle rock can deform and creep a little like very stiff putty. Small parts melt where temperature, pressure, water content, and chemistry allow it. Those local melts feed many volcanoes. So where did all this internal heat come from? Some of it is ancient. Earth formed about 4.5 billion years ago from dust, rock, metal, and larger bodies colliding under gravity. Every impact carried kinetic energy. As the growing planet compressed, that energy became heat. Dense iron sank toward the center, while lighter rocky material rose, releasing more gravitational energy. Early Earth was not assembled gently. Much of that original heat is still escaping. A small object cools quickly because it has a lot of surface compared with its volume. Earth is huge. Its interior contains an enormous amount of thermal energy, while the surface through which that heat can escape is relatively limited. Thick rock is not a perfect insulator, but it is slow. The planet has had billions of years to cool, and still has a long way to go. Pressure often gets credit for the heat, and that answer is only partly useful. Compressing material can raise its temperature, so the compression of the young Earth did create heat. Material moving deeper can also warm as pressure increases. But static pressure is not a furnace that continuously produces free energy. If nothing is being compressed, moved, transformed, or reacting, pressure alone does not keep adding heat forever. A second major source is still operating today: radioactive decay. Tiny amounts of uranium, thorium, and potassium are mixed into Earth's rocks. Some isotopes of these elements are unstable. When their nuclei decay, they release energy. The emitted particles and radiation interact with surrounding matter, and that energy ends up as heat. One atom contributes almost nothing. An entire planet containing these elements for billions of years is another matter. This is natural radioactivity, not a buried nuclear reactor in the usual sense. There is no giant chamber of glowing uranium under the crust. Heat-producing elements are spread unevenly through the crust and mantle, often at concentrations measured in tiny fractions of the rock. Uranium-238, thorium-232, and potassium-40 decay slowly enough that significant amounts still remain. Scientists are still refining exactly how much of Earth's heat comes from radioactive decay and how much is leftover heat from formation and later differentiation. Estimates depend on models of the crust and mantle. Detectors such as CAMLand in Japan and Borexino in Italy have even measured geoneutrinos, hard-to-detect particles produced during radioactive decay inside Earth. Those measurements suggest radiogenic heating supplies a large fraction of the planet's present heat loss, roughly half in many models, but the exact split is not settled. There is another contribution at the center. Earth's inner core is solid and slowly growing as the liquid outer core cools and freezes onto it. Freezing releases latent heat, the same basic kind of energy released when liquid water becomes ice, though the materials and pressures are completely different. The separation of lighter elements during this process also helps power motion in the liquid outer core. That moving, electrically conducting iron is important for more than temperature. Convection in the outer core helps generate Earth's magnetic field. We know the outer core is liquid partly because earthquake waves behave differently when they pass through it. Pressure waves can travel through solids and liquids, while shear waves do not pass through liquid. The solid inner core exists despite being even hotter because immense pressure raises the melting point of iron. Heat then works its way outward. In the mantle, hotter material tends to become more buoyant and rise, while cooler, denser material sinks. The motion is slow, often measured in centimeters per year, but over geologic time it rearranges oceans and continents. Cold tectonic plates can descend into the mantle at subduction zones. Hot material can rise beneath ridges and volcanic regions. The system is messy, and plate motion also depends strongly on gravity pulling dense slabs downward. A kitchen pot is a tempting comparison for mantle convection, but it can mislead. Soup is liquid and moves in seconds. The mantle is mostly solid and turns over across millions of years. A better clue is a bent shelf that sags under weight. It looks rigid during a normal day, yet given enough time and stress, solid material can deform. The timescale changes what solid means. In volcanic regions, heat reaches shallow depths unusually efficiently. Magma rising through the crust carries thermal energy upward. Water can seep down through cracks, warm against hot rock, and return as hot springs, steam vents, or geysers. Places such as Iceland and Yellowstone have high local heat flow, but for different geological reasons. In Hawaii, fresh basaltic lava erupts at roughly 1100 to 1200 degrees Celsius. That is deep heat arriving at the surface fast. Move far from active volcanism, and the gradient can be much lower. Old, stable continental interiors often have different heat flow from young volcanic provinces or spreading ridges. Rock type matters, because some rocks conduct heat better than others. Groundwater can carry heat sideways or upward. A temperature reading in one borehole is not automatically a rule for an entire country. Not always, of course. This also explains a common confusion about ground source heat pumps. A shallow system used to heat or cool a building usually relies on the ground's stable near-surface temperature. Much of that shallow thermal stability is linked to solar heating and seasonal averaging, not a direct pipe to the fiery mantle. Deep geothermal power is different. It targets hot water, steam, or hot rock at much greater depth, where Earth's internal heat is the main resource. Globally, Earth releases roughly 47 terawatts of internal heat through its surface. That sounds enormous, and it is enough to make geothermal energy valuable in the right places. Yet sunlight delivers vastly more energy to Earth's surface system. Internal heat powers geology, mantle motion, volcanism, hydrothermal circulation, and part of the engine behind the magnetic field. But it is not the main reason the surface is warm. No one has drilled anywhere close to the core. The deepest boreholes reach only a little over 12 kilometers, about 0.2% of the distance to Earth's center. Temperatures deeper down are inferred from seismic waves, laboratory experiments at extreme pressure, the chemistry of rocks, magnetic behavior, heat flow measurements, and physical models. The estimate of 5,000 to 6,000 degrees at the core is not a thermometer reading. It is a carefully constrained reconstruction, so the ground beneath us gets hotter for several connected reasons. Earth is still losing energy left from its violent formation. Radioactive elements continue to generate heat inside its rocks. The inner core is crystallizing, releasing energy and helping stir the outer core. That heat escapes slowly through a planet large enough to hold on to it for billions of years. The cool soil under your shoes and the hot iron at Earth's center belong to the same thermal story. Near the surface, weather wins. Deeper down, the planet's own history takes over. Every hot spring, deep mine, volcanic eruption, and warm borehole is a small leak from a world that has been cooling since before the first ocean formed, and is nowhere near cold yet.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!